To start, for the afternoon session, we have Wenwei, who's going to tell us about deep thermalization.
All right, thank you so much. Thanks to Isaac and Joan Young for this wonderful conference, for organizing this, and thanks to Kias as well. Thanks a lot also for the very good food that we've had over the past 2 days. I'm sure we have a lot more great food as well. So I'm getting very fat, as you can see. All right, so today what I'd like to talk to you is about deep thermalization, which is a work that I've been working on for the past few years, as you can see from the long list of papers here, done in collaboration with wonderful collaborators. And so I'm sure many of you have heard of this topic, deep thermalization, before, but what I'd like to do today is to give you a report of our latest understanding of how to think about deep thermalization. In particular, our focus, well, I'll give a comprehensive but concise overview of what the framework is, but I especially want to get towards the works which are newer, which talk about a general theory of deep thermalization in the presence of conserved charges, symmetries, and generalized maximum entropy principles. So I think this work is very apt for this conference because it's a novel form of quantum equilibration coming from the lens of quantum information. All right, so let me start by placing the work in a bigger context. I'm sure many of us agree with this statement that quantum simulators have enabled new explorations of new kinds of physics, and they come in many forms. What I'd like to impress upon you is that there are two features of them which make such explorations very interesting and very exciting, which is that one, they have a high degree of controllability. You can program interactions, you can control them, you can isolate them from the environment, and you can drive them out of equilibrium very well. Secondly, they also have this very new kinds of ways of taking data, global site-resolved measurements. We can go in there, take snapshots, understand how each atom or each spin is behaving, very different from a traditional solid-state system. So this gives us access to new regimes of physics. And indeed, in the recent past decade or so, 2 decades, there have been many, many novel physics discovered in the realm of quantum simulators. I've only given you a very, very short list. So things like time crystals, which rely on driving the system out of equilibrium and achieving a new kind of phase of matter, which is not possible in static systems. Then, of course, there's this MIPT, measurement-induced phase transitions, the change in the entanglement structure of quantum states as you intersperse measurements with unitary dynamics. Then we can also go beyond just standard hydrodynamics in terms of full counting statistics. We can ask about fluctuations of local charges, how they're distributed. And all this relies on these capabilities of these measurements. So this talk is no different. So I will talk about an example of novel physics that also utilizes such features, which is deep thermalization. And the main idea that this is quantum thermalization beyond local observables. This is quantum thermalization in the set of local post-measurement quantum states. And this is very related to the works to the idea that Robert, for example, talked about yesterday when he talked about trying to certify states using trying to certify global states by measuring everything except for local regions and summing over them. So essentially what you can think about deep thermalization is the physics behind such local post-measurement states. This might help in such algorithms and protocols, hopefully. Okay, so the outline of the talk is as such. First, I'll talk to you about the framework of projected ensemble, which is a framework in which we can talk about deep thermalization in quantum spin systems. I'll talk about the emergence of deep thermalization, which is this new form of universality. And then I'll talk about how to understand them, or the emergence of such ensembles from the point of view of quantum information theoretic principles. So a generalized form of the second law of thermodynamics. I'll especially impress upon you the role of symmetries and the measurement basis in determining such limiting forms of the distributions. And then I will also try to explain to you that deep thermalization is not just related or not just constrained to quantum spin systems, but it occurs much more generally across physically distinct systems like Gaussian bosonic continuous variable systems. And time permitting, I've only one or two slides on this. I'll talk about some very recent work on extending the framework to the framework of mixed states when your measurements, your dynamics have errors like decoherence, and then you get mixed states, you can ask about mixed state deep thermalization as well. So feel free to interrupt me with any questions in between. Okay, so let's begin by talking about quantum thermalization, just a standard regular one. And this is a basic question of how do you get irreversible stat mach from reversible quantum dynamics. And the standard setting that we are interested in is suppose that we have a global pure state, say initially all spins pointing up or down, some simple initial state, and it undergoes some sort of quantum chaotic unitary evolution. As you know, the state remains pure, but the spins become rapidly entangled. Now, at the global level, there's no form of steady states because the state is just continually evolving. But what happens is that if you look locally, say on this A region, you bipartition the system into A and B, you look at the reduced density matrix, then there could be a form of universality, which is that we expect, and we can also confirm in many cases that the state, local state goes towards a universal form called the Gibbs state. And I stress that this is universal in the sense that it doesn't quite depend on the full microscopics of the initial state. It only depends on things like the conserved charges, the amount of energy it has initially. So only symmetries and conservation laws affect the final form of the state, not the actual microscopic dynamics. Furthermore, we also have very good principles to understand the emergence of such Gibbs states or universal states. So we can think about the second law of thermodynamics that was taught to us in StatMech. And in this case, it turns out that you can argue for the appearance of such Gibbs states by saying that this should result from a minimization of the free energy, which in the case for this mixed state is the maximization of the von Neumann entropy. So it's very nice. We have a good physical understanding for why they should emerge. The question I want to ask is there physics beyond this framework? Okay, so let's look at the regular quantum thermalization again. The way to think about this reduced density matrix is that this is the marginal quantum state of a full global quantum state. So imagine that this state contains the entire information of the universe, but we're only looking at it locally. That's marginal. What happens instead of looking at the marginal state? Sorry. So in constructing the marginal state, what's being assumed here is that the path is not accessible. And this is the role of the trace, right? We are ignoring all degrees of freedom outside A. We can relax this. So this allows us to think about the conditional quantum states weighted by how often they appear, the probabilities. So the main idea is this: we have the same dynamics, but instead of just ignoring everything about what's happening outside the region A, let's do some measurements on B, which we can do using the global measurement capabilities of quantum simulators. Suppose we measure in some basis, Z, and I'll talk about what the role of the measurement basis is. But then what will happen is that suppose we get a bit string, the state on the A, instead of being mixed now, will be collapsed to a pure state. So this is a conditional state that depends on the label of what you've measured. If you repeat the process, you get a different conditional state. If you repeat the process, you get a third conditional state, and so on and so forth. And all in all, there are many, many conditional states. We can collate all of them into a set of the states together with how often they appear, and this is known as the projected ensemble. Okay, so this is a pure state quantum ensemble. How do I think about them? So some properties of the projected ensemble is that you can have an idea of them in terms of geometry, in terms of like how they are distributed in Hilbert space. So imagine that we have this circle, which is a projected Hilbert space. So the projected ensemble can be thought of as a distribution of pure quantum states on this space. So all the points refer to the different projected states, with the mean value of all those points being exactly the reduced density matrix. And so from this point of view, you should really think of the projected ensemble as a physically motivated unraveling of the reduced density matrix into constituent pure states, which are motivated by measurements, right? So in that sense, the projected ensemble is a strictly more encompassing framework than the framework of the reduced density matrix. So next question. So here are the fundamental questions that we can ask about the projected ensemble. We know from regular quantum thermalization that we go towards a universal Gibbs state, but now we can talk about the full distribution itself. Is there some form of limiting ensemble that it tends towards? Taking the appropriate limits, of course, we have to make sure that we work in the appropriate, say, thermodynamic limit when we have many, many measurement outcomes, and presumably at late times because we want the system to achieve enough complexity over time. And more importantly, or importantly as well, are these universal ensembles. What do I mean by universal? So I want to make sure that these are ensembles that do not depend too sensitively on the microscopic details of the initial state, just like in regular quantum thermalization. Because if, I could construct this projected ensemble for any initial state, any global initial state that I wanted, but that will require an exponentially large amounts of data for a big system. I want a theory or some prediction in which I can compress all this data into something that is small and therefore make it thermodynamically meaningful. Okay? Second question is that, well, clearly the answer to the question is yes. Otherwise, I wouldn't be talking about this topic. So how do these limiting distributions depend on, say, symmetries of dynamics? Say that we have, say, conserved charges or energy in the state or over time. And how do they depend on the choice of measurement basis? Because in this case, the difference between the different measurement bases may learn more or less about the charges that are present in the state. And that might affect the distribution or will affect the distribution that emerges. And thirdly, is there also a similar physical principle that we can argue for that underlies the emergence? Okay, so what I'd like to explain is that now our most updated framework is the idea, or what I like to think of the projected ensemble as, is a particular quantum communications protocol, which is very physical. So the projected ensemble can be thought of as an encoding of classical data, ZB, the bit strings, into quantum states. So imagine this. We have two experimentalists. One is Bob and one is Alice. And Bob is going to represent the bath, okay? And Bob and Alice share the global quantum state. So what Bob is going to do is that he's going to measure on his region and get a bit string. And in doing so, the global quantum state is going to give Alice on hand a small quantum state, local quantum state, which encodes what the ZB is. And this, of course, occurs with probability P of ZB. This is 100% a bona fide quantum communications protocol. It just so happens that is mediated by this global quantum state that we began with. All right? And this is very nice because now we can ask this information theoretic question. How much information can Alice extract from the quantum state ensemble, where she receives this projected ensemble, which on average has this average mass H, which is the density matrix? So there are some, okay, so the answer to this question, you can go back to quantum information textbooks. I should put a reference here. But the basic idea is that we're going to look at the accessible information of the quantum state ensemble. And so what Alice can do on her hand when she receives the local quantum state is that she can try to measure. She chooses some sort of measurement basis, a POVM, and then she measures, and she gets some measurement outcome, M of I, that depends on this POVM set of POVMs that she chooses. And she tries to ascertain what label that Bob has sent to her. So there's, of course, if you understand entropy and information, then there will be some sort of mutual information between the encoding in the ensemble and the information learned from Alice. And just to flesh out very quickly how this is calculated, the mutual information. So prior to measuring, so Alice did not only has understanding of or has a model for what the global quantum state is. And so she has some prior belief that this bit string is being sent with some marginal. So she has some entropy, there's some entropy associated with these messages. But after measuring, then she can update it to some posterior belief. And then so she gains information. And so the average information gain is the difference between the entropy initially with minus the conditional entropy, right? So that's the mutual information. And the accessible information is when Alice decides to choose the optimal POVM over all the sets of POVMs. So you take a supermem over all the POVMs. And this is the maximum amount of classical information extractable from the quantum state ensemble. And so this will be our guiding principle to understand the physical object that emerges in natural quantum dynamics. But it comes from a very quantum information point of view. So some interesting facts about the accessible information is that it's not too large and it's also not too small. So it depends on, there are bounds, upper bounds and lower bounds on it. For a given quantum state ensemble with mean rho, the upper bound is very well known. So that's given by the Hall level bound. And that's nothing more than the von Neumann entropy of the mixed state. And so this is just, the usual formula, sum of lambda k log lambda k. And physically, what amounts to, or how do you get this ensemble is if you encode the classical data into orthogonal quantum states, then it's quite clear that Alice just reads off or just measures in that orthogonal basis and just reads off the information. She has 100% correlation between her information and the classical information encoded. But maybe what's not so well known, but now is becoming more and more well known, is that there's also a corresponding lower bound called the subentropy. And again, it's a function of all the eigenvalues of the density matrix. So it's again a function only of rho. And morally speaking, you can think of that as being encoded by states which have overlaps. So it's a bit hard for Alice to really decipher what message Bob is trying to send. Of course, Bob has to send a message which respects the mean value being rho as well. Okay, so there's some non-trivial distribution that emerges here. Physical question now we can ask is, for the case for states evolved using say a Hamiltonian or quantum circuit, what value of accessible information should we expect the projected ensemble to harbor, right? Yes, please. Right. So you can of course generalize the framework to include randomness in the measurement basis. But I think physically for me, I would like to fix a particular measurement basis and understand what structures emerge from that. Yeah. Thank you. Okay. So let's think about what the expected accessible information could be or should be. So for one, we know from the standard theory of quantum thermalization that the mean value is the thermal state, assuming that regular quantum thermalization happens, ignoring all this integrability exceptions and so on and so forth. But we can also look at the structure of this global quantum state then. So without loss of generality, we can think of the Schmidt form of the global quantum state as being like this. So there's two parts. One is the density matrix that encodes the thermal state, and then one is this scrambling unitary that encodes the change of the Schmidt basis between A and B. So basically, it's a mapping from A to the system B, and this is the Schmidt unitary, right? And so we should really think of this as the isometry or the unitary that encodes the classical information, which is the Schmidt basis. Now, in the projectile ensemble, we're also going to measure. So we're assuming that it's measured in some local basis. And so we can see that a key tension is happening here. There's a tension between the measurement learning basis, which is how much information we're extracting, and the Schmidt basis, which is the scrambling of information. And this two will determine the information theoretic property of the projectile ensemble. This is a very heuristic argument, but this is the idea behind how we can argue for the expected accessible information of the projectile ensemble. So our first prediction will be as such. Nature should be thought of as quantum chaotic, generically speaking, barring exceptions, and scrambling. Those are the words that we often throw out. And so if my measurement basis is incompatible, which I will not define very fully here, but you have a sense in which this is true. If it's not compatible with the encoding basis, then we expect minimal accessible information transmission, right? And this, I would argue, is the idea of deep thermalization. So what that means is that we are trying to argue that the projectile ensemble should tend to the ensemble that attains this lower bound. So our job now is to ask, what is the ensemble E that equals Q of rho in terms of its accessible information? Okay, so that's our first prediction. So we can now answer the question of what's the principle to formulate for deep thermalization. We can formulate this so-called generalized maximum entropy principle, which is based on, I guess more precisely, the principle of minimum accessible information. So we're looking for this state ensemble, pure state, in which this S, which is a negative for the accessible information, just to make it maximization, is maximized, such that we know what the mean of this pure state ensemble is, rho A. This is a well-defined mathematical question, so I can answer that just purely from math, right, from QI techniques. It turns out that this was solved already in the early 90s or mid-90s by, of course, quantum information theorists, Joseph Robs Wouters. And this is known as the Scrooge ensemble. Okay, I will give an explicit form of it in the next slide. But pictorially, you should think of it this way. It is an unraveling of some density matrix in a way that respects the mean, but which is comprised of pretty much overlapping states. And here, this is a true bona fide coloring of the distribution for this state on a Bloch sphere, for example, for a qubit state. And the reason why it's called a Scrooge is because, as you know, Scrooge is a very stingy person, doesn't want to give out, money or presents. So this is a most stingy ensemble that doesn't give out information. Okay, here's the definition of the Scrooge ensemble. So E of Scrooge, it depends on the input rho. So given a mean density matrix rho, we can try to draw quantum states in which its probability density is weighted by its overlap with the density matrix. So here, this d phi here is the uniform Haar measure. So essentially, we're weighting states that are more towards the highest eigenvalue of the largest eigenvalue of the density matrix. And then for every psi that we draw, we're going to create this normalized state, which is a rho distorted state. Morally speaking, you can think of it as the state cooled down by this density matrix square root of rho. So imagine if your rho was a thermal state, e to the power minus beta h, then square root of rho is e to the power minus beta h over 2, roughly speaking. So it's cooling it down in some fashion. And so the Scrooge ensemble is then defined to be the ensemble of pure states in which you are drawing these normalized states according to this distribution. Okay? All right. So this is a highly non-trivial ensemble distribution, but there are some limiting cases which are very nice. One example is the case when rho itself is really maximally mixed. So in this case, intuitively, it's clear that the Scrooge ensemble is the Haar ensemble, which you can write down mathematically exactly. It looks like this. And so what that means in terms of the predictions is that if you believe in this principle, then the projected ensemble in the appropriate limits for systems that achieve regular infinite temperature thermalization should form a quantum state design, which we've heard a lot about over the past couple of days. So essentially, the projected states the statistics of the projected states should mimic Haar random states better and better. You can ask about the similarity at different moments and that they should agree, right? As a function of, say, how long you evolve the system for and how many measurements you're doing, because we're taking the thermodynamic limit. Okay, so let me just give you a list of the so far, the summary of what we have achieved so far across many different groups in the world in terms of the emergence of universal ensembles. And I'm just going to state for you the results. I will talk about a toy model in the next slide. So in the case for Haar ensemble, we can ask, where does it appear? And there are many, many cases when it appears. So the simplest case to understand is, suppose that you have a global Haar random state already. So then we're not talking about dynamics here, we're just talking about a random matrix state. We just pull out one global Haar random state on n qubits and look at the small system and construct a projectile ensemble. Naturally, you would argue that this should also be itself Haar random for a generic instance of this global state. And this could be proven, this was proven by Jordan Kotler and company in this PRX in 2023, which also introduced the framework of the projectile ensemble. And then more relating to thermalization itself, then we can talk about Hamiltonian evolution and say circuit evolution. So I've worked a lot on the circuits part of things. So we have actually proofs in the case for dual unitary circuits that this achieves the projectile ensemble achieves deep thermalization to the Haar ensemble for the case for dual unitary circuits. And people like Amos Chan and Andre De Luca have also proved it for the case for random quantum circuits as well. For the case for Hamiltonians, suppose that we begin from an initial state that has energy which is in the middle of the spectrum. So we expect that regular thermalization is to infinite temperatures. Then caveated upon the fact that you're measuring in some incompatible basis with respect to the energy, so which means that the measurements do not pick up the energy, have zero expectation values in terms of the Hamiltonian, then they also saw numerically that this converged the Haar ensemble. And in fact, there were experiments done in a group of Manuel Andres and Caltech on small systems of Rydberg atoms that also proved or showed that there was also convergence to the Haar ensemble. And lastly, you can do the same framework as in the case for ETH, where instead of looking at dynamics, you can just pull out an energy eigenstate from a quantum chaotic Hamiltonian, repeat the same process, and you can also see that this occurs. So I'm just stating all the summary of the results so far. I haven't given you any numerics, but trust me on this. Now for the Scrooge ensemble, then we can repeat the same thing. So we can prepare an initial state with some non-trivial energy and measure in some, again, measurement basis which does not reveal the energy. And what they found, this papers, was that the Scrooge ensemble emerges at the appropriate temperature beta that you care about. Okay, any questions? Yes, please. Yeah. So the definition for Scrooge ensemble doesn't depend on whether or not it's a qubit. So this D is on the NA qubits that you care about locally. So big D in this case would be 2 to the power of NA.
Have their own energy. Should I picturize if it is close to one state that each I have a block sphere defined by all bases, and each basis have the energy defined by energy expectation value of the basis state and distribution of.
Right. Okay. So in the case when your subsystem is not just a single qubit, then of course I cannot draw this picture exactly, but you should just morally think of this, that there will be some cartoon of the Hilbert space on A. Okay. And then in this case, in this summary slide, this measurement basis was assumed to be energy non-revealing. So which means that every time you measure on the B system, you don't know about the energy of A. And what will happen is that then your states will start to populate the A Hilbert space in a way which is most ergodic according to the minimum accessible information principle. And that's it. So each state does not carry any more information about the energy fluctuations. Yes. That's correct. Yeah. Yeah. So sorry, maybe I should have chosen a different zeros as opposed to this one. Correct. Correct. But importantly also that the measurement basis does not reveal the energy. And I'll talk about how to incorporate such behavior afterwards. Yeah. I'm sorry? No, because like take the Ising model, ZZ plus X and plus Z, let's say, right? You measure the Z basis, you will know something about the energy, right? Because your interactions are on the Z basis. If you measure in the Y basis, then it doesn't reveal the information. That's what I mean by non-energy revealing, is a basis. Yeah, even if only partial. Generic basis will be energy revealing because there will be some overlap with the energy density operators, for sure. So in these cases, I would say that these are fine-tuned numerics then. For energy, maybe it's a bit difficult because they're non-commuting, but for on-site charges, then yeah, you can do that. Yes. Yeah. So I'm not sure. It depends on the microscopics. Yes, please.
If I do not measure with the basis, but if I measure with the scrambled basis, it is like as if we are acting a random part circuit on top of each exponential minus IHT. So do you expect to have infinite temperature?
Yeah. So precisely. So if instead of measuring the fixed basis, suppose you do some additional scrambling here, then I think what will happen is that in the case for Hamiltonians, you still have energy conservation, right? But you just not learn anything more about the energy of the state, so you'll get the Scrooge. So essentially, a scrambled basis in which you measure it is the same as an energy non-revealing basis. All right. So let me give you some intuition for at least in one case, and I'll just present it in like 1 or 2 slides because this is kind of old work, but how deep thermalization emerges in a minimal model. So in this case, we're going to look at dual unitary circuits. And these are very special circuits which have this notion of space-time duality. And let me explain what they are. So think of a 1D circuit, brickwork circuit. So the blue boxes are unitaries, two qubit to two qubit unitaries. Unitarity means that U and U dagger, they become identity. Of course, that's a definition of unitarity. But additionally, it's supposed that the tensors can be contracted in a way, sideways, and they still become the identity. Then this is called dual unitarity because they are unitary in a sideways direction as well. And what this buys us is that then we can kind of like change time and space and think of the circuit as also being evolved sideways. And that's the flavor of it. I don't want to go into too much details. So our main statement in these papers from a few years back is that we can rigorously prove that after sufficiently long times, and in fact, this long times is not long in the global system size, but only in the subsystem size, the projected ensemble can be rigorously proven to be hard random. Because in this case, circuit evolution would give rise to infinite temperature regular thermalization. And the key idea, as I've already mentioned before, is that if we turn the circuit sideways, we can imagine that there's unitary evolution going this way before it comes out that way. But what the measurements are doing is that they are random. And so you're going to have some random field that is being toggled at the boundary. And this gives rise to a stochastic random quantum evolution. This sideways evolution is reminiscent and in fact equivalent to a form of measurement-based quantum computation because we're doing computation through the bulk, but this is stochastic in this sense, and that's why we explore the entire Hilbert space of A in this case. Basic idea. Okay, so let's move on to the role of symmetries. Oh, sorry. Yes, there's a question. What if the boundary is periodic? You mean if you connect the chain up this way? So in this case, I think you can still do the trick. So you can think of two computations sideways, and then you can redo the calculation. There'll be some corrections to the convergence or changes in the statement, but the ultimate physics is roughly the same. Yeah, thanks for the question. Okay, so here's the new part of the story on deep thermalization. So we wanted to understand how does deep thermalization change in the presence of symmetries and measurement bases? I mentioned that we talked about incompatible energy non-revealing measurements or measurements that don't reveal the charges. So this was our initial theory was predicated on that assumption. However, measurement basis surely matters when there is a conservation law. And to give a very explicit example, suppose that we have a state with a definite charge Q with on-site symmetry in a Z basis. So how many particles there are, or how many spin-ups versus spin-downs. And suppose we do a Z measurement. Then if I obtain a measurement outcome ZB, I can understand how much charge there is in the B system, QB. And so definitely I also know what the state on A has collapsed to, QA. So that means I can additionally label the projected ensemble with an additional quantum number, Q of A, and additionally, the ZB is the label of the charge within the sector. So we can expect that the limiting form would no longer just be simple Scrooge or simple Haar, but it should be something more like a direct sum ensemble in which within each charge sector, it is more or less, it is uniform, but then each charge sector occurs with a certain probability. So a convex combination of the different distributions over the different charges, right? But conversely, you can take the same state and measure in the X basis. And in this case, measurement X does not tell me or update my information more about what charge there is on A. And we can expect again, a simple Haar ensemble or row of A. In the case when, say, the state is at infinite temperature. Okay, so we're not assuming any particular energy in this case. All right. So clearly you see a difference here. And our aim here is to now talk about a general theory accounting for two things. Like two things can matter. One is that in this simple example, I assumed that the initial state had a definite charge. But let's relax that and allow for arbitrary charge fluctuations in the initial state. So that's going to be encoded by this distribution over the charge sectors P in for input, P in of Q, and some state in this different charge sectors. Secondly, we want a theory that also accounts for the compatibility or incompatibility of the measurement basis with the charge basis. So in this case, the charge basis was in a Z basis. Here, clearly, there's correlations. In X, there's no correlation. So we want something that can account for any basis that we care about. Okay? So here's now our most updated theory of deep thermalization with charges and arbitrary measurement basis. So the settings as such, suppose that we begin from an initial state that has some charge distribution, so on and so forth. So same thing happened this morning. Okay, so then now let's have it undergo charge conserving scrambling dynamics. So in this case, I'm assuming the charge is some U1 charge. And then we're going to measure an arbitrary basis. And suppose we get an outcome nu. Okay, I'm going to call nu as anything in between x, y, z, still local, of course. Okay, the key point is that when we get a macroscopic outcome nu, we're going to get different. Okay, so if you get macroscopic outcomes nu1 versus nu2, each one of them corresponds to different projected states, psi of nu1, psi of nu2. But it turns out actually that the microscopic measurement outcomes can be grouped into equivalence classes. It turns out that even though for a single realization of the generator state, you will get two different projected states, on average, you might learn the same amount of information on A. So what I mean to say is this. I can say that microscopic outcomes nu1 and nu2 can be are defined to be the same equivalence class if they give rise to the same state rho of this nu, which is the equivalence class, on average over different generator states of the dynamics. So here you have to kind of stretch your imagination and think that there's a natural ensemble as well here in which we're averaging over that allows us to declare that microscopic outcomes nu1 and nu2 are on the same footing. And the picture is this. If you draw or if you get a microscopic outcome belonging to one class, then you might get some updated information of the charge QA on the local subsystem A that depends on what you've drawn. And this amount of information should be the same regardless of, as long as you are drawing outcomes that belong to this equivalence classes. So in the case when there's a U1 symmetry, then you can ask how many equivalence classes are there? There's only at most order n, so if you have two symmetries, maybe n squared, poly n basically. Okay, so each different measurement outcome will fall into different equivalence classes and they will update my information about the charge on A. Importantly, the amount of charge on A is not definite, right? It's only definite if you measure in a very specific basis. So there will also be some charge fluctuations on A itself. So that's why I've drawn it this way. Next step is to argue or to posit that the projected states from each class is itself drawn from the maximally entropic ergodic distribution, which is a Scrooge related to the amount of information I know in this class. So with this class, I can know what the mean value of my charge is, and then I can unravel all these states, say here on the block sphere, according to the maximally entropic distribution, which is a Scrooge distribution. Okay, and I can do that for each equivalence classes. So pictorially here, rho of nu is the average state for each class, the star. And this psi of nu is the individual microscopic states that belong to each equivalence class. And the last step is to then say that we have a ansatz where my projectile ensemble as a whole is just a convex combination of all these Scrooges according to how often you see each equivalence classes, and that is known as the generalized Scrooge ensemble. Yes, please.
Two different measurement of the same equivalence class, like should we expect them to give us exactly the same Pauling distribution or approximately? Like if it's only approximately the same, then how can we like this up into those concepts?
Right. So in this case, when we define equivalence classes, we're saying that nu1 and nu2 yield the same state, exactly the same state. But you can also relax that to say they yield the same state up to some, epsilon error in trace distance, for example. And that allows us to then make an approximate ansatz as well, right? But the key point here is that the same state will be on average over different generator states, right? But we are making a statement about a single instance. So that there's a bit of a leap of faith that you have to do here. We assume that the global generator state itself has some underlying ensemble distribution, but we are pulling out one state from that and constructing the projected ensemble. But we're saying that each measurement outcome can behave the same over this this initial ensemble of global states here. That's how we define the equivalence classes. Yes, please. For a fixed measurement, yeah, so for fixed measurement outcome nu1 and nu2, big two measurement outcomes, we say that they're equal or equivalent if they give rise to the same state on average here. Right. Okay, so this is a theory, physical theory, and you can ask, can we prove it? We can analytically derive this under some replica trig assumptions and under some more assumptions. So it's not a rigorous theory, but at least we can give some, calculational arguments for it. And one more point I want to point out is that this generalized exclusion ensemble I claim is universal. And I want to stress again that this is meaningful from the thermodynamics point of view, because the only information that you need is the initial state distribution, which is a poly n data. You don't need extensively many, you don't need exponentially many measurement input to get this generalized exclusion ensemble. So from the point of view of thermodynamics, this is very sensible. And this is what I argue to be the generalization of your regular thermalization. Importantly, you see that this requires information beyond just the mean value. So it takes in all information about the higher moments as well, but still this is a very small amount of information. Okay, so the key point, if that construction was a bit too elaborate, is that we have a limiting distribution which is maximally ergodic in this accessible information, quantum information theoretic sense, up to information of the initial charge distribution and information learned from measurements. And we have a full theory that accounts for all of that. So this is a very, I guess, natural and sensible way of formulating how we should think about the distribution at the end of the day. Yes, please.
Unravel this ensemble or according to each measurement outcome in the same equivalence class.
Right. So I'm saying that each each projected state that depends on the microscopic label is, you can figure out what class it belongs to, and then it's one of these states. So suppose that it's in this class, then we can say that its distribution is this. If you see a different microscopic outcome, it belongs to this class, then we will say that this belongs to this distribution. And each one of them occur with different probabilities.
How many equivalence classes exist?
So that depends on this. That depends on symmetry. So suppose that you have a global U1 symmetry, then there only n, exactly n plus 1, I guess. N. Yeah.
So it's just labeled by the total, like a committing set of charges.
Yeah. Oh, sorry. My bad. Sorry. The equivalence classes depend on how many, so here I'm assuming that I'm measuring in the uniform basis. No, not charge basis, some arbitrary angle. It doesn't have to, so I'm trying to develop a theory which is arbitrary measurement basis, right? So Z is the charge basis, X is the charge non-revealing basis, but I can allow for any direction. So within the direction, I just count how many up downs in this direction I have, and then that defines the number of equivalence classes.
So for example, if you measure everything in a Z basis,
yeah,
then will be a NA? Or...
Yes, it will be NA, correct. Yeah.
If you measure everything X basis, it will be just
one. Exactly. So it will reduce to the examples I gave in the previous slide. So in the case when you measure the Z basis, this histogram is just sharply peaked. This histogram is just sharply peaked. So that will reduce to the direct sum ensemble. In the case for the X basis, then all microscopic outcomes belong to the same class, correctly.
What's a bit maybe so there can be is there only I would say is equivalence classes like continuously labeled or is it always discretely labeled?
Discrete, I think, because
theta is a continuous variable, while x versus z gives a 1 versus n. So then I'm a little.
Yeah, I mean, I guess
It's continuous. Well, it seems like the number of equivalence classes.
Yeah, so I guess the correct way to say is that for generic measurement basis is poly n, and at specific points it reduces to NA and 1. But generically it's just poly n. Yeah. And the number of equivalence classes is to do with how many bit flips there are in the new basis. Like new meaning not up basis, but just a tilted basis. Yes, please, Ethan.
Maybe the discussion was too fast, but when you say it's thermodynamically being like in thermodynamics, we have order 1 frame.
Right. Okay. So then I'm defining it to be not exponentially many. So
It's not thermodynamics, right? Like you be screwed if you had all the n parameters to describe it.
that's a fair point. Okay, so perhaps I should not use thermodynamically meaningful, then I should use maybe from the complexity point of view, like easy to construct.
Here, like the charge example, like the charge is just one continuous
Right.
But I think you're saying it's not labeled by the mean.
Yeah, so to construct this ensemble, the target ensemble, you need to sum over n such equivalence classes, poly n such equivalence classes. So I agree with you that maybe if you want to say that this is not thermodynamically in the same way of saying order 1, that's true, but at least it's not exponential. More precisely, you don't have to keep track of every microscopic bit stream. I guess that's the point. To construct classically the target ensemble.
But it still makes sense.
Yeah. So we right. So we can try to do that as well. And I think this would be the way to go for energy conservation. Yeah. Great. Thanks for the questions. Yeah. So let me show you the one and only numerics I have here, which is that we have numerical confirmation. It works really well. So let's take this situation where you have an initial state, which is a product state of, say, plus theta minus theta plus theta minus theta. And theta is this angle that's freely tunable. So it just tells me like initial state, how many, like which direction I'm pointing in. But on average, the amount of charge here is 0 in a z basis, still 0. Okay, and then I'm going to scramble the dynamics or scramble the initial state using a U1 symmetric Haar random unitary in the z basis. Okay, so my initial state is off, kilter. My dynamics is U1 scrambling, and then I'm also going to measure in a off kilter basis as well. So with labeled by an angle of theta out, so a different angle away from z and x. These two angles can be different, theta in and theta out. And what I'm going to plot here is some distance measure between the distributions. I don't want to go into detail for what it is, but this is just looking at the kth moment of the state ensemble with the target ensemble and looking at the trace distance between them. And what's plotted here is a sequence of trace distances for different system sizes n. So larger system sizes, thermodynamic limit is here, over here. And this color plot represents how close we are to 0. And the closer we are to 0, the closer the ensembles are to the target ensemble. And this color plot represents the y-axis is theta out, and the x-axis is theta in. What you see is that regardless of what the value of theta in and theta out is, there's always convergence to the generalized Scrooge. And this seems very uniform. In fact, it is uniform and is exponential with the system size with 1 over square root of 2. 1 over square root of dimension, sorry. Yes. K in this case is 2, sorry. Yeah, but it's also true for 1, 2, 3, 4 example. Okay, any questions here? Good. Okay, so the last 10 minutes, let me quickly run through a different physical system. So previous studies and all this framework has been talking about quantum spin systems, and there's a notion of a local bounded Hilbert space. What would be really interesting is to ask, do I find the same universality in a physically distinct system? Can I apply the same principles of generalized maximum entropy and quantum information theoretic principles to predict similar but different behavior in this? So we will consider bosonic Gaussian CV systems. In this case, we are looking at bosonic modes. They have unbounded Hilbert spaces, and there's no notion of a local high random state. So this is, in some senses, quite non-trivial. Right, for the experts, we also know that there's no notion of a two design in a CV system. Okay, so to give you guys a crash course on what Gaussian CV quantum systems are, we're looking at n bosonic modes, and similar to the quantum spins, we're going to look at a subsystem K, A of K modes, where the remaining modes serve as a path B. And the key object in describing CV systems is to look at this Wigner function, which is a quasi-probability distribution on the phase space. So here's an example of it. I'm only drawing this for one mode, but imagine that there's a Wigner function on the n modes, which is too hard to draw. We will focus on the case when my input state, the global state, is a bosonic Gaussian state. So what that means is that this Wigner function is just a multivariate Gaussian. And we know that Gaussians are fully characterized by its displacement, its mean, and its variance, which is given by these quantities, R and Vij, which is the matrix of covariances relating to the expectation values of the quadrature operators. So morally speaking, we are looking at the multivariate Gaussian. Now, when you want to measure a Gaussian CV system, you can preserve Gaussianality by measuring in a Gaussian basis. And that involves a choice of a covariance matrix sigma B on the B system. And so the POVMs here will be, as such, they'll be projectors rank 1 on the phase space on the B system. And they all sum to 1, as we know from completeness of the POVMs. But there's a choice of how we measure the system. This sigma B represents the amount of like squeeze, not just squeezing, but squeezing also, but the amount of like squeezing in different directions that we are measuring in. So the important point is that now, if you measure in a Gaussian basis, each conditional state on A is then itself also Gaussian because we are closing the dynamics. It has itself a displacement vector, RA, and covariance VA. And this occurs with probability P of RA. So pictorially, you can think of it this way. Every time you prepare this initial state, this big initial state on n modes, you measure in this Gaussian basis, you will get one outcome at random, and that corresponds to 1 point here, 1 point here, 1 point here, 1 point here, so on and so forth. And this is the phase space of the RA system, the A system. Now, if you look at the Wigner function, if you focus on one of them, this covariance describes the squeezing in this phase space for this single quadritional state. So the question, okay, so the projectile ensemble then is described by only two pieces of information. One information is how are these displacements distributed, P of RA? And secondly, what is this covariance matrix that corresponds to correlations between the modes in the A system? So our setup for Gaussian CV system is as such, similar to the case for quantum spin systems. We're going to imagine that we have an initial state, which is a product state on this n modes, squeeze light with zero displacement, but is squeezed, so they have a mean boson number. And then we're going to evolve it by some deep or random linear optical elements, which consists of beam splitters and phase shifters. So that preserves the boson number. That's our conserved quantity, but it's going to kind of like mix the modes up and entangle them. And then we're going to measure in the Gaussian basis on B using some choice of sigma B. And the question we want to ask is there universality in these pictures, in this projectile ensemble? What should we expect the limiting form of the projectile ensemble to be? So we can then invoke our maximum entropy principle again So again, we want to maximize the entropy, which is negative of the accessible information, subject to the idea that my mean state is a thermal state, which we can expect just from regular dynamics of a CV system. So that's given by this e to the power minus beta Na, which I've already talked about, with this temperature set by the mean boson number. So we proved in our paper, following seminal works by Holovo in recent years, that the Gaussian Scrooge ensemble, which is the analog of the Scrooge ensemble for quantum spin systems, is the unique ensemble having the least accessible information. And that's given by a distribution of displacements, which is just simply normal with no squeezing in different parameters, just isotropic, and also no squeezing and no anisotropy in the correlations between the different modes. So essentially, all forms of entanglement are destroyed in the conditional states, projected states. The projected ensemble is just a collection of unsqueezed coherent states. So you get maximally classical states appearing fully, not just at a mean value thermally, but also for each constituent state. This is just a completely disentangled state between the different modes in A. So we can show this, and we prove this, in fact, for random Gaussian CV modes initially, and then we can see that numerically for deep quantum circuits, deep linear optical circuits as well. And this represents the extension of deep thermalization to Gaussian CV quantum systems. Okay, so it's very good that our principles not only work for quantum spin systems, but also work for bosonic CV systems. Okay, lastly, in the last 5 minutes, I'll just have one more slide, which is on the topic of mixed-state deep thermalization, which is a recent work we posted with Xiehang Yu and Pavel Kos from MPQ. So we are asking the question, we know that quantum devices are hardly perfect. In my formulation, I assume that measurements are going to be perfect, projective measurements. My dynamics is unitary as well. But we know that inevitably there exist errors in unitaries or measurements. And so perhaps some decoherence channel occurs. How will they affect the universality of deep thermalization? So we studied a very, very simple scenario. And of course, this is just the beginning of our analysis. So we considered loss as a simple starting case. Of course, there are many, many more extensions to this. Oh, it's okay. Yeah, I have one more slide. Okay, thanks. I think it's fine. All right. All right, so we considered loss as a simple starting case, and in removing some of the measurement outcomes, so imagine that we have A and B again. If we did not have the loss, then we would condition A on all the measurement outcomes on B, but let's assume that we lose some information of the measurement outcomes here. So the conditional states on A will become mixed naturally because we have now loss of information. And the question we want to ask is, how will the mixed states be distributed across over the space of density matrices on A now? And we find using some dual unitary calculations that there's an emergence of universal mixed state ensembles that depend on how many measurements we are losing. And so this is perhaps not too surprising. You just simply have a hard random state on the bigger system of NA qubits, the one that you have, and M qubits that the ones that you're losing, sorry, like D qubits you're losing, sorry, qubits, sorry. And then you just trace out the M modes that you do not want. So that gives rise to an ensemble of mixed states. And this is known as the generalized Hilbert-Schmidt ensemble. And lastly, we also showed that if you look at the quantum information theoretic properties of each conditional state, you ask, can it teleport information from one end, suppose we leave one end open, to this end? Can it teleport information with knowledge, with loss of some information in the middle of the chain? Then we find, using calculations of conditional mutual information, that there's a quantum teleportation transition with the number of degrees of freedom lost relative to the system size A. So if you want, I can talk more about this afterwards. Equal. So when the ratio M over A, NA is 1 or above 1 or less than 1. Okay, so in conclusion, so I've tried to impress upon you that there's a novel form of quantum equilibration universality appearing in quantum simulators called deep thermalization that goes beyond standard quantum thermalization. It's underpinned by generalized maximum entropy principles that are coming from quantum information theory. And I presented to you a rich host of different physics that arises due to symmetries and measurement bases. And if you forgot all the details, the take-home message is that we have new paradigms in quantum many-body dynamics and physics coming from QIT, which is very interesting. Some of the open questions involved, what are the different mixing times or design times in achieving deep thermalization? Because I didn't even talk about how quickly they get there. I only talked about the limiting ensembles. Are there connections to, say, information scrambling, quantum error correction, and how complex the states I can get from sampling from such distributions are? Those are also very interesting questions. And I also alluded to the fact that perhaps these random states could be useful to understand protocols in quantum information science, like for shadow tomography, which requires generation of random states, or even in certification, which Robert talked about yesterday. So perhaps our insights, physical insights, can give some ideas of how his certification protocol behaves under the assumption of the emergence of such universal ensembles. So with that, I'd like to acknowledge my collaborators and thank you so much for your attention.
In the CV, oh, sorry. In the CV case,
Yeah.
I just didn't totally understand the statement of the results. Did you choose the maximally random ensemble of Gaussian states? Or the maximally random ensemble of all states? Because you got Gaussian states in the end.
Right. So the setting is that we preserve Gaussianity in everything. Initial
Okay.
state was Gaussian, measurements were Gaussian, therefore the conditional states were also Gaussian.
I see.
And so
Okay.
the question is like, how do we understand the limiting form of that ensemble of Gaussian states?
I see.
And the only constraint we have here is the mean boson number that we input, which plays the role of the number of, well, which not only plays a role, but is the number of particles in the system.
I see.
Yeah.
And so I guess you could also
It's fine,
ask
it's fine.
about the maximally entropic ensemble of any state, like, or any unitary, not necessarily Gaussian.
Right. So that becomes much harder because
Okay.
then the Wigner function requires all
Sure.
moments. And I think that's an open question.
I see.
Right.
I see.
Because in this case, we can compress all the data down into two pieces of information, just the mean and the variance. But now if I want to talk about universality in this picture, so I need to fully characterize how it looks like.
I see.
Right, which is difficult.
But is it correct to say that like these Scrooge random ideas are maybe the right way to extend designs to CV systems?
I would think so. I think that's the philosophy I was trying to argue for, that you would want to employ this principle. I didn't mention this, but we invoke our maximum entropy principle assuming Gaussian states.
Yeah,
Okay,
okay,
so,
that's the part
so sorry.
yeah.
Yeah.
No,
So
no.
sorry.
No, thanks. That's
Yeah.
cool.
Yeah, I just have a general question about what do you really mean by thermalization of a free system?
Well, equilibration of a free system, I guess. Yeah. So if you take a say this n modes, and then you have a definite boson number, and you just scramble the basis in the linear optical sense. Locally, you still look like a thermal state.
You mean like in the single particle basis?
Yeah.
I wonder how quantum is this, because like can we also think about the analog of classical with random permutations in U1 cases? Like because like mixing times they're all well defined on probabilistic theory, so maybe especially for U1, can I just think about I have n number of balls and I randomly permute them, and measuring with theta basis seems to be weird in classical example, but can I find some analog on classical theory? Or so like is it I'm trying to understand how distinct this is from the classical permutations.
So you're saying how distinct is it if you assume dynamics was classical, but measurements were still quantum?
I mean, like,
Okay, so I'm like, let me try to explain. So in this framework, we're looking at an ensemble generated by some random process, right? So in this case, I'm looking at the random process generated by measurements, and the probabilities are given by the bond probabilities. So of course, you could ask the same question for any classical process that gives rise to random outcomes or
Yeah.
trajectories, let's say.
yes.
You could have a random walk, and you can ask what's the distribution of those random walks in that space, underlying space. So from that point of view, the framework of ensembles is not tied to quantumness,
Yes.
but the projected ensemble is tied to the fact that we are using quantum measurements to learn something about the state. You could ask the question, what happens if you have classical dynamics, say random permutations on my state, but I measure in a quantum basis. And in fact, this is work that I'll be posting soon. Yeah.
Okay.
Like, does that answer your question?
Maybe I'm thinking of, can we also define deep thermalization on classical permutations? Does
Right.
that even make sense?
No, it makes sense, but how would you generate randomness there? So you could have the randomness coming from the choice of the permutations. That's perfectly fine. But then they'll be asking questions about what the distribution is of this random walk in the permutation space. So here I'm fixing the dynamics and then using measurements as a way to generate the random states.
I see. Thank you.
Yeah.
We may talk about this afterwards,
Sure.
but have you considered what might happen if you extend your notion of measurements to not just be single site and potentially, multi-site measurements and even non-commuting measurements? What would the projected ensemble look like in that case? Like, what would you?
Right. I think if your measurements are still local to some degree, the same universality should apply. But of course, once your measurement becomes more and more non-local, then you may start to learn about the encoding basis, right? As a very extreme example, suppose you measure in a Schmidt basis, then you definitely know what it's basically knowing with 100% certainty what the state on A is then. So that would destroy any hope of universality. So universality necessarily requires some amount of loss of information, compression of information, and that necessarily comes from the incompatibility of my measurements with the scrambling basis.
If I can follow up quickly on that, then would you expect that there would be some enhanced effect, again, if you say we had like non-commuting measurements? So now the order is important to defining your projective ensemble.
The order is
Measure overlapping measurements on different sites.
right.
And if you measure in one order, it will condition on the results possible for the next measurement.
Right. So that will be more along the lines of trying to incorporate MIPT into this framework, which you can, because now you're saying that measurements itself are going to affect the state dynamically, besides using it as a label for in MIPT, and this is the same thing, right? It's just that in MIPT, we're looking at measurements in the bulk of my space-time circuit. Here, I'm just looking at it at the very end of my circuit. So you can definitely try to push a few measurements down below from the boundary, and that there'll be a hybrid deep thermalization MIPT kind of framework.
Yeah, thank you.
Yep.
Okay. Well, I did have one question. So this thermalization timescale for
Yes.
deep thermalization,
Yes.
should we expect for let's say 1D or 2D local interacting system? What is should we expect them to be different from the normal thermalization time? And if so, what is the reason?
Right. So what I can say is that because deep thermalization is a hierarchy so if you look at the different moments, you need thermalization at the first moment before you can get deep thermalization at the second. So any higher moment time is definitely going to be larger than the regular thermalization time. In the case for DUs, we proved that they were all equal. In the case of random unitary circuits, there's actually a log K dependence. And you can argue for that using line tension calculations and also some like random matrix calculations. In 2D, it becomes much more interesting because you also have the notion of a teleportation transition fighting you as well. So above a certain depth, then all of a sudden, all measurements might affect the behavior of the local subsystem. So then maybe this spread in design times might not be present anymore in higher D. So I think it's still highly interesting. I don't really, we have only very basic results on the design times for 1D circuits, invoking arguments from purification dynamics and also like line tension calculations.
Okay.
Thank you.
Yeah. Let's thanks Wenwei again.